Thank you, everyone, for attending our talk on almost unlimited C++ and kernel mode applications. And you may be wondering why you're here. I'm sure it's because you're expecting death, destruction, mayhem, and panic, because that's sort of what you get when you program in the kernel. And if you did not believe that, obviously we can step back in time and see some quotes. Now, I did not verify these quotes. I did not change these quotes, but urban legend says they're true, right? 25 years ago, maybe it wasn't a good idea. And this continued on with saying exceptions are bad, memory allocations, we don't like to see those. I have plenty of coworkers that malign C++ for the same reason, and it's problematic for me. This doesn't help. This popped up about 20 days ago. The left-hand side says, I'm going to call through a function pointer do. It's never actually set to anything, but the compiler has assumed that never called was executed at some point because otherwise the program would be ill-formed. And if you can read the disassembly on the right, you see that it's going to remove all the files, or at least attempt to. So if you're here the rest of the week, Wednesday and Friday, there's a couple of other talks on undefined behavior. Now, 2004 was a very interesting year, evidently, because Windows had some discussions about programming with C++ in the kernel as well. The bold here is my addition. And it explicitly says that while we may not expect to use C++ in the kernel, given the right implementation and the right execution environment, all things are possible. 2012, to jump ahead a little bit, Visual C++ wound up getting this little option. And I know game programmers I talk to love to disable exceptions, love to turn off RTTI. New and delete, we're back to there. The only problem here that I see is that we also limit the instruction set that we can use. So if we really wanted to do something other than maybe a print driver or network driver or something that use the full capabilities of the CPU, we're out of luck. Unless you might do some own assembly programming or other things in the kernel. How lucky am I? It's just a blue screen. I'm sure we've all gotten them. Okay, so in 20 years of programming flight simulation, this is a smattering of the different environments that I've either directly worked with or read code from. A lot of them are Unix-like. The three bolded ones are very interesting. We're going to use Windows, Visual C++, and try and do something real time. And the first one there, on time, is different than the other two in that it is a pure operating system. For the end time and RTX choices there, the system actually boots to Windows. So there is an operating system on subset of the cores. Then you have this other operating system sort of hanging out in your system, not quite virtualization, but it's taking the rest of your cores. And that's where all the magic happens. Now, boost. As of 1.6.4, these were the platforms that were in the platform directory. I did not look at 1.6.5, sorry. It covers half of my list from the previous one. For that end time and RTX Windows options that I had on the previous slide, those are mostly going to be directed at Win32 here because they are trying to emulate the Windows API. All right, has anyone here actually done Linux real-time programming? Okay, we got one hand. Pretty common diagram. It did not take me long to find these. I could have found plenty more. Basically, we look to do things like separate your non-real-time processes from your real-time processes. The image on the right shows explicitly doing real-time on half the cores and non-critical applications on the other half. So I will directly ask Jeff, pretty common? This particular?
I don't know, I just did it for the first time recently.
Oh, for the first time recently? It's pretty common, Jeff.
Okay.
So for Windows in real time, obviously Windows itself is not going to be real time. But if we look at these two extensions, InTime and RTX, they're really a lot alike. They're pretty much limited to the Intel and AMD architectures. They do the same thing that I showed on the previous slide. They want to segregate CPUs that are doing real time from the other CPUs. There's a big problem though. In a lot of this real-time work, we don't have latest NIC hardware. We have lots of old CAN bus stuff sitting out there, and that really is low-volume stuff, and it a lot of times does not use latest interrupt architectures. So these two particular solutions don't allow you to share interrupts between two devices, between a real-time device and a Windows device. And it gets worse. Even something like a PCI Express bridge chip that might take an interrupt can't be shared with one of these devices, which is a bummer. Likewise, you see here that shared libraries are an issue. These two platforms want to explicitly deny you all access to Windows DLLs. And then there's the big difference there. InTime wants to do user mode, lots of protection, and RTX doesn't. So I hope you can see where we're going here. If we're going to talk about C++ programming in the kernel, and I've highlighted things in bold, we're probably going to be talking about RTX. This is an image out of the InTime documentation. Being a user mode application, they look very much towards separating memory spaces between the processes. And that gives them a higher level of reliability. RTX, though, being down in kernel mode, not so much. Shared memory across the board, Windows apps, RTX can all access the same memory. Driver creation under RTX, much simpler than anything you would ever do in Windows. Pretty much, you make one function call to register an interrupt handler, and that's it. Now, a couple of weeks ago, there was this conference, and one of the consumers of flight simulators didn't have some very good things to say about the products they've been receiving, to the point where they really do not want a Windows product anymore, whether it had an InTime extension or an RTX extension. And some of these things that they list here are not even real-time related. iOS here is an instructor operating station, not the Mac operating system. Pure Windows application, they're saying that they hate their product, basically. And of course, my response to them would be, okay, you want Linux, but there's plenty of examples where you can do bad things. Yeah, the Toyota brake case scandal. Anybody have a Toyota? Nest thermostat. Lots of cold people. All right, so there's a book that's on the table from Chris, who I will not attempt his last name, talks about real-time C++. And he, in the preface, talks about the CPU environment that he works with, and that's much more towards the microcontroller. So small memory size, small code size, yeah. But that's not what we're going to work with. Lots of cores, lots of memory. For a flight simulator, airplane in general, you have lots of distributed systems, sensors all over the place, lots of black boxes. And from a simulation standpoint, that same vendor that didn't like having Windows also doesn't want to have a lot of boxes that they have to boot. So they really want you to bring in all of these simulations of different pieces and put them onto one system. We have lots of cores now. We have a real-time operating system that will take advantage of them. Go for it. So, talked about an operating system, talked about CPU architecture, compiler, we'll certainly be using Visual C++ in this talk, and there's this issue of freestanding versus hosted. If we were only going to stick with the freestanding 16 headers there, absolutely no problem, whether it's in user mode or kernel in this particular case. The other headers, yeah, not so much. And that's where most of this talk will be going, is talking about the problems that we encounter in some of these other headers. Okay. Random device. Start with something simple. Very simple application. We just want to potentially access a piece of hardware to give us random numbers. For Visual C++ 2012, the constructor calls an external function, which winds up calling rand_s from the C runtime, which looks for RTL gen random via DLL. And of course, that fails.
Didn't you say something about no sharing of DLLs?
I most certainly did, Marshall. Keep that thought. So for 2012, we return E no mem. Exception gets thrown, we can handle it as was shown in the previous example. If we jump forward just a few years to one of the newer Windows 10 SDKs, rand_s changed just slightly. Now, there's this system function 036. Of course, we all know what that is. It's basically a synonym for the RTL gen random. In making this change, they also said there is no fallback. Windows will always have system function 036. So we abort now, and bad things happen. So yes, Marshall, you asked about shared objects. For working in Linux, kernel module, access other kernel modules, everything's great. Windows, if you're in a kernel export drivers, all that stuff goes together. RTX, yes, no DLLs, different entry points, etc. But we can still fix this, sort of. We can supply our own rand_s. System function 036 is available. And for the infinite test that I ran of 2, it always returns 0. So no random numbers there. Most likely solution here is just to write rand_s, always return E no mem, be done with it. So let's move on to the file system. I know for bare metal, very constrained systems, we probably don't have a file system. Most likely, we're just going to put our data into memory. It's at address, whatever, zip through it. But here's the basically equivalent of what the file system specification says for file size. Basically, we're going to call stat, we're going to get the size of a function and return it. So for RTX, this winds up giving us 8 unresolved externals when using the Windows SDK. This is a little interesting because if you looked at this implementation, you'd find that find close happens to be in an unnamed namespace with a couple of structs and type defs that aren't even used. So we have a false dependency. Peak name pipe, we might want to stat a pipe as well as a file, so it's in there too. Stat, if that were the only problem, maybe work around it, but there's more. We have no environment either. So we have no current working directory, which means we have no relative file paths. We have no directory traversals, and on and on. So from the standard level, Titus Winters and a few others came up with this proposal to say, file systems in general are a problem. We might want to do some user injection of file systems for testing. I talked to Titus in Toronto, and there's a possibility whether I implement a full file system specification or something like this, if I really want those things to work, still up in the air. Path. Another part of the file system that's part of our vocabulary in some respects. For 2012, 2013, Microsoft shipped an implementation of path that was just pre-technical specification. The character type was char, header only, path worked well. 2015, 2017, got a rewrite. And now we have this dependency on some external code. The external code winds up bringing in lots and lots of file system related APIs from Windows that just aren't available. So No file system functions, no path. We're back to probably mapping files into memory and going from there.
Just showing how the file systems, file calls fail.
Yes, Marshall was making a comment about not having a file system. Having file system functions fail is perfectly within the standard. Correct?
Yeah.
Yeah.
So we'll have to say, no, fail.
All right. Random numbers, file system. How about threading? Anybody want to guess how well threading is supported? It's a pretty simple example. We're just going to create a thread that does nothing, and we're going to join on it. Yeah, so for 2012, we wind up with 17 unresolved externals. Got a little better for 2017. Microsoft changed their runtime from using their own concurrency runtime to making direct operating system calls. Still a lot of unresolved externals. If you deep down in the layers of the Microsoft runtime, you'll see that creating a thread winds up needing to do some sort of synchronization at the thread creation level. So it's got mutexes and condition variables that are going on. And RTX has a history of about 20 years, and they never had the need for a condition variable. So immediately that one's out. Mutex, they implement the Windows APIs for Mutex, but there's something else going on there that makes that one problematic as well. Duplicate handle. We're in the kernel. We don't duplicate handles. It's just the thing. So that's a problem as well. Boost, though. We have to congratulate Vincente for his work. Only 3 unresolved externals for the same example. The first one, though, is actually available in RTX. And the second one, we want to know how many processors that we could use for concurrency. So we get a call in to get logical processor information. The third one's kind of interesting, local free. Down in the system error, when we call a message for system error category, it winds up needing to call format message on Windows to take the error code and get a message back. And if you don't pre-allocate the memory, that function will allocate it for you. If it does that, then you have to call local free. Okay. Microsoft, in their implementation, though, does something a little differently. They go ahead and pre-allocate the memory, and they do it twice. First time is a narrow allocation. The second time, they're actually calling format message W. So they get a bunch of W chars, convert it to narrow, and on up the chain. Yeah. Okay, so we're still in threads, stacks. Windows kernel, 12 and 24K, RTX 8K, very small amount of work that we can do in that. Although, quite powerful amount of work if you think about it. Currently, for thread and standard, we have no way of actually changing the stack. And there's at least 2 proposals that talk about at least exploring the idea of, are there requirements that we should capture and do things to expand on our capabilities with threads. Other problems that we have here, there's no stack guard pages. So if you've got 8K, 16K, whatever, you go off the end of it, you can keep going. However, since this is Windows, Visual C++, RTX, from a testing standpoint, we can jump back over to Windows and create our threads with this stack size param as a reservation. So when we say 16K, 32K, whatever, you do get a guard page on Windows. So you can test. If you go over, exception pops up, I need to create my threads with a larger stack size. Likewise, there's no memory protection. So if everyone's ever dug into address sanitizer, you'll see that at some point it's doing something to manipulate the pages in memory to make them read-only. Not going to work here. All right, so summary on RTX and C++ concurrency. Atomics and lock guards work really well. Just about everything else, very problematic. And Gore was supposed to be here. Coroutines, again, very problematic. The compiler is going to have to generate calls behind the scenes for you. Just won't work. Call once I'm listing here as being unknown because it should work. We're going to investigate that a little bit more. Very simple example. We have a function with a static, and we have to do a constructor call. If you compiled this in 2012, let's say, you get something like this disassembly. There's two function calls in there. One's to the constructor, the other is to add exit. Not a lot going on. However, in 2015, a new default was added, thread safe init. And if you look closely at this disassembly, you'll see that there's an init thread header and an init thread footer that's going on. We're also accessing TSS. Lots of weird things going on here. And in this particular case, when I tested this the other day, it actually crashed the application. So, not good. You can disable this. ZC thread safe init minus, it's gone. Clocks. Another of the real-time functional areas that everyone has to do something with. This is pretty much the same example that you'll see from Howard Hennett and Stack Overflow. It's in the real-time C++ book, a few other places. Our time duration here is 100 nanosecond units. Windows pretty commonly uses that. In some cases, I've seen people implement these clocks using the timestamp counters, just an RDTSC for Intel. And that's great. Fast access, as long as you stay on one core, you're guaranteed of having timing numbers that you can believe in. Once we start going off cores, then there is no real synchronization between these two. In the case of having Windows and this other extension, we see Windows start, try and synchronize all the TSCs, and then some point later, this other operating system starts up and decides it wants to synchronize all of its cores. So now we have this large delta T between two operating systems that are sharing the same system. There's lots of other timing sources in your PCs. There's the DRAM refresh clock. There's the USB clock. This one was introduced in about 2004 and gets really squirrely. Even if you have 64-bit Windows operating systems, a lot of times it is put into 32-bit mode. And it's more expensive to read time values from this. But they are going to be one single clock value. All your cores will be fine. We're going to go through a little bit of the implementation that I was working on for this many years ago. And this implementation, it took the view of I'm in the kernel. Obviously, nobody else is using this. So I'm going to enable it. And when I'm done with it, I'm going to disable it, set it back to 0, because I can. Anybody want to guess what happened? Odin? So I'll give you a helper here. There's two operating systems. I just made a big assumption that I'm in control. I really should have done something like this. If you're familiar with the title of this slide, it comes from the movie The Day the Earth Stood Still. So if Windows is over here using this particular source for its clock, and you go and set it to 0, you're rebooting, or you're waiting however long it took for your system uptime for the clock to come back around and catch up. Exceptions. I have absolutely no problems with exceptions, even in real time. Part of that's because of other developers. Certainly being in the kernel, I want to know when things happen. And we have a very simple example here. An example that I see quite a bit. The string that's passed in, once we throw the exception, needs some place to live other than, well, it's a string literal. So a copy winds up being made of this string. So we wind up allocating memory to hold this string. We've already in an error case, we're throwing an exception. We've probably jumped out of our real-time deterministic execution. Now we're going to allocate memory. In this case of Windows RTX, Windows in time, your memory still basically comes from Windows. It has to know what's available. So whenever we allocate memory like this, we have to do some bookkeeping back over to Windows. As it turns out, we have to complete all other threads that might be ready as well before we do the jump back to Windows. So now we've had an error condition, we've decided to throw an exception, we've needed to allocate memory, and we just destroyed our timing sequence because we executed everything out of order. Pretty bad. Possible solution, just create your own exceptions that return the string in this case. So now, we still have the error case, we're going to throw an exception, but we're not going to allocate, we're still going to execute in order, and at least some of what we expected will still occur correctly. The other part of exceptions, getting away from the standard. On Microsoft, if you didn't know, we have set unhandled exception filter. If you compile everything with /eha, which is a different mode of exception handling, you can actually catch things like floating point exceptions, access violations, stack overflows, etc. If you also happen to be in 64-bit land, you can do a pretty good job of capturing all your registers in your stack backtrace. So in order for reliability, this would be something that you'd want to build in, and it's something that's very possible. Now in Boost, just recently, Anthony provided a nice library to do stack traces, and there's at least 3 options that are available for Windows. In this particular case, though, the first 2 that actually try and do something with the stack both want to use COM. We're in the kernel, no COM. Okay, so another library that's not available to us. Well, unless we just want no hops. Other problem with being in the kernel, completely different loader than what Windows is using. Completely different loader from what Visual Studio and all the debug tools was expecting to be used. So now you've got addresses that are nowhere close to what your PDB thought they were going to be. So in this particular case, we're having to compute offsets, not actual addresses, and then post-process our stack traces with those offset information. Short break here. Talked a lot about various things within the runtime. Modules really better not cause any more heartache here. They shouldn't be. Unfortunately, right now, Microsoft's implementation, since we're talking about Visual C++, is only providing the DLL runtime versions of the interface libraries. It's not a technical issue. It's the only thing that they've put out. They're not supporting RTX, so they wouldn't see this as a must-need to put that out, but small issue right now. So we've talked about C++. In this particular case, there are at least 3 other languages that I've managed to stick into the RTX environment. Fortran, quite a bit. D, not so much. Certainly possible, and I've had several functions from D working, but I won't say that I'm an expert in D. Lua, though, perfectly acceptable to link into the kernel in this particular case. There are some pieces of Lua that are file system related, imagine that, and I forget the other piece, that do create problems. But if you just want to use a Lua script and do some things, no problems. Okay, so much like C++, we're going to do a little dissection here of the Fortran runtime. Math functions, Fortran certainly wants to use math functions. In this case, Intel Fortran not optimizing the code. Most of the math functions can be satisfied with the C runtime. There's, let's say, in the order of 10 that can't be. If we look at strings, it's a little different story. The Intel compiler for Fortran generates at least 3 runtime calls to do comparisons, concatenations, and copying of strings. And if you've ever worked with Fortran, things get interesting with strings because we want to pad with spaces at the end instead of null termination. And so comparison and concatenation winds up with some quite strange algorithms. Compact Fortran, slightly older than the Intel work, didn't have any problems as far as needing runtime calls. It just implemented everything right in line. Fortran compilers, recent years, have also had modes where you can enable bounds checking. And of course, when a bounds check violation occurs, it wants to call into some error reporting function, and the error reporting function wants to pop up a dialog. It doesn't happen. Compact Fortran did not have such an option. So in this particular case, taking Intel Fortran, compiling that into kernel, provide a few math functions, provide the 3 string functions, and provide a little something for error reporting if you're in the bounds checking mode. And speaking of bounds checking, with newer Intel architectures, we have some new registers, some new instructions, and we can do some of this in hardware. And since we're already implementing our own thread library, evidently, we can then just add this as well. Currently, if you've got an application that's trying to use MPX, you wind up having something else setting out there that's hooking the create thread call so it can create all the necessary resources to do this particular work. And if you happen to be on GCC, it's an interesting conversation that popped up on the mailing list recently. I guess I have not used this on GCC, but there was a perception that they were going to deprecate this. At least one person thought so anyway. And upon posting a change to deprecate it, the response was, no, we aren't deprecating it. I don't know what's going on. So it's still in GCC. If you continued on the mailing list trend, it said that it is problematic in some ways, although it did not go into details. For Visual C++, this got added in Update 1, and you can give the nice command line option there of D2MPX, as well as adding the additional resources to hook the create thread calls. So performance monitoring. Absolutely none of the applications that you might want to use are available to you since you're running in the kernel. And that doesn't mean that you still can't compile your code for Windows, compile for Linux, run the same applications. But hey, we're in the kernel. We can execute read model-specific register and write model-specific register. So we can actually implement our own perf, our own Intel PMU, our own vTune, whatever we want. Likewise, you can go out to the memory controller and get your bytes read and bytes written. You can look at cache management. You can deal with quality of service, I/O, and on and on and on. In the case of performance counters, you don't really have the restrictions that you had with the HPET that I showed earlier, in that the model-specific registers are per CPU. So we can actually collect per thread, per CPU, whatever we want. Memory controllers, a little different. That's per system. If you have one CPU, it's per system. So if you've got Windows and RTX setting in this system, you're going to have both. And I'm going to be done really early, so I hope you have lots of questions. You didn't ask any while we were going through. So the purpose of this particular talk really was to try and enlighten, I guess, to let you know that sometimes you're given scenarios that really don't work together. And the Microsoft Visual C++ team is not supporting RTX. Interval 0 is not really supporting Visual C++. So it's, as a developer, I have to do all of these little things, like providing a randos if I want it, providing a thread library if that's needed, modifying boost if that's the decision that we want to make. And with that, I will open the floor for questions, and Odin will walk up to the microphone and ask his question.
You mentioned that you are testing by compiling to Windows proper that has a page guard to detect like Stack Overflow. But two questions there. If you're doing customizations like swapping out calls to DLLs or kernels or whatever, you're not executing the same code for one, and especially in light of exceptions, you're probably not following all theoretical possible paths. So how are you sure that you saw max step depth?
So the first part, if I'm testing in Windows, I'm not exactly testing what I'm running. Absolutely correct. And I will say that I spend quite a bit of time trying to make both environments as close as possible, so that I can say that I am executing as many of the code paths that I would in both environments. The second part was
like
with
so something
exceptions.
throws that could potentially be, thinking Machiavellian case, a longer exception, a deeper stack than if you didn't throw, or if you have some really weird,
So, you'd like to say that post-initialization, absolutely no exceptions are ever going to occur, right? And so our call stacks will always be the same, and our timing information will always be the same. It will always work the way it's supposed to. Now, that's not the case. Some people will use exceptions for flow control. Very important to monitor the system. I mean, if you're not monitoring, you don't know that somebody has done these type of things. So being a library developer, I'm not going to be reviewing millions of lines of code to know where somebody actually decided to throw. I can report that an exception occurred. I can provide the framework so that all of the timing is always being done, so it's constantly monitoring the system to know if something is executing not the way we expected it to. And that's pretty much my answer, is that at some point, everybody has to get on board and accept that if you're throwing exceptions, you're starting to go outside the bounds of what the system was intended to do. Yes, Jeff?
Did I understand you to say that you were using Fortran in kernel mode? And if so, what was the application?
So 20 years of flight simulation, there's even another 20 years of Fortran code out there. Yeah, lots and lots of Fortran code that when you start talking about having an aerodynamicist program who still knows Fortran, the execution environment has been given to them. They're totally unaware of that. They compile the Fortran code, it produces an object file, it gets linked into something, and off we go. If you switch to something like MATLAB instead of programming directly in Fortran, then you've got super code bloat and other issues. But yes, as Marshall was commenting, and once you start going through code generators that produce lots of code, then you have a whole another set of problems. So yes, Fortran definitely. It's in 20 years, it's been trending away from Fortran. More people view Fortran as being a dead language, and so from a personal standpoint, they say, I want to do something that's more modern. I want to use C++. Yes, sir.
I'm just curious. I mean, in Windows and TOS, to deal with long call stacks, or sometimes when, like in case of file systems or networking, it's hard to control how deep going to be stacked. They introduced, you can request another stack. As long as you control those points where they can expand, you could do that. Does it work for you, or it didn't?
So, dealing with the stack, yeah, pretty much you can do whatever you want to. If I had wanted to, I could have put in my own code that detected how far we were going in the stack. Oh, we're about to cross a boundary. Let's do something else here. But that gets back to Odin's question about what are we testing? Do I want to produce more and more code that I have to test that may be different between the two environments? Or do I want to sort of do some faith here and say, I will test it in Windows, I will have the stack guard. Once I've got results, then I will switch back over. Now, if we start talking about a flight simulator, switches all over the cockpit, you can't test everything.
Sorry, I probably missed this part, but when you're saying switch back between what two environments are you switching? User mode and kernel mode, or Linux and Windows? Or?
So Windows would certainly be user mode. Most of what I was talking about was dealing with kernel mode.
Okay.
Yeah, so if I'm in kernel mode, I can manipulate the thread block however I wanted to and replace stacks and do pretty much what I wanted to. I don't want to do that.
Oh, but it's a standard API now. It's not that you have to do that. It's just...
It's a standard API in Windows.
Yeah, okay. But in the Linux there is another case.
In Linux.
Okay, got it. Thank you.
The other side of the room can ask questions too. Yes, sir.
What is the problem to deal with coroutines?
Coroutines?
Yes.
So a coroutine to the user looks like a normal function, would you say? I mean, you don't see any explicit calls to anything to, well, you've got the awaits and yields and things like that. What the compiler generates for those particular spots in the allocation, yes.
Okay, we still have allocations.
So this borders more into the business side, not the technical side, in that coroutines is quite new. When we talk about a real-time system, we tend back into the old beliefs that, oh, only C can be used. I've got this legacy compiler that's never being updated, on and on and on. The operating system that I was showing and talking about, RTX, it tends to lag behind. So even if I was using coroutines, there is a very good chance that whatever runtime calls were needed to make that coroutine work weren't going to be available. So you would get unresolved externals as well.
My understanding is that coroutines, the only thing coroutines are supposed to use is a call to view. That's not really. That limits let's say, that limits what they are allowed to do. Just had a talk with Gore, and he said that basically this pretty much the only way it can be implemented from his point of view.
So I was hoping that Gore was going to be here so that we could have a little more discussion on that. If you want to talk to me tomorrow, the rest of the week, I'll code something up and give you a more definitive answer. Yes, Odin.
You mentioned in the beginning that you were working in like kernel mode callbacks or IRQs.
So for the interrupt handlers?
Yeah. I don't know how the Windows kernel works, but don't you have like a really hard deadline of how much time you can, or you know, how much, how long you can take in a?
So from the Windows side, we're a general purpose operating system. We don't want to delay, we don't want to give an unresponsive environment to a human user. Most of what I've been talking about for a flight simulation, there's no real user involved as far as through a GUI. We're processing I/O, we're computing equations of motion, etc. So in that particular case, the interrupts are still an issue. We certainly don't want to delay some of our execution because we're handling interrupts. And I think that really gets back to knowing the system. And I can say, writing your own network stack, writing your own network drivers, when somebody plugs in another system on your network and all of a sudden you're getting spanning trees and other things, if you're not detecting those things, all you know is your system sort of becomes unresponsive. So again, that gets back to my response about we're monitoring these things. We see, oh, all of a sudden we've got more interrupts per second. All of a sudden our interrupt time has shot up. Something's going on and something needs to be done. It's kind of funny because when you report these things, saying that, hey, you know what, somebody is sending me ARP every now and then, but you know that system's not on this network. Some people sort of take offense to that. It's like, well, you know, I'm using the operating system that everybody else is using. You're not. And you're the person that's telling me I'm in trouble. And it's like, yes, because you are. Does that answer your question enough?
Pretty much, yeah. I guess one sort of variation on it, like, how do you reason about, you know, longest theoretical processor use?
So worst case execution.
Yeah.
I think some of the people that I've worked with say that I just sort of walk out and put my hands on systems and go, yeah, it's good. But that's not what should happen. In some cases, there are systems that are, so the flight simulation itself is much more tolerant, let's say, of higher jitter.
Yeah.
Systems that are much higher frequency, that have hardware in the loop, they aren't. But we're running the same software in both cases. So we sort of use that hardware very intolerant system as our baseline. And if we can do that one, then everything else should fall out from there.
Okay, but it's still just guessing and then testing, essentially. Yeah.
Yeah.
Okay.
Guess and test. Yes, Scott.
Yeah, I feel your pain. I mean, I work on a lot of strange consoles and things, and ROSs are not really standard, and we end up with similar issues here and there about using fancy C++ features. So interesting talk.
Thank you.
What do you end up doing about much of this stuff is kind of my question, though.
Are you asking, do we contribute back to Boost so that everybody could do this, or?
Sure.
So,
for example, what do you do about it?
so as far as
I know, we
Boost,
do.
I will say that in the past, I've talked to plenty of Boost developers, and I've said things like, oh yeah, I don't use Boost. Mm-hmm. And the example that I showed for Boost Thread actually was worse, let's say 10 years ago. Mm-hmm. There were more unresolved externals. It's gotten better. And that's a big generalization. I don't use Boost. Boost is huge. Certainly not everything in Boost uses the operating system. Mm-hmm. So there is plenty of Boost that could be used in this particular environment. Beyond, what do I do? Try and keep the hardware as long as possible, much like a console. Try and keep the compilers the same as long as possible, which gets back into our, oh, I'm a new developer in school, I was using a newer version of Visual Studio, why aren't we using that here problem. Hardware, operating system. Likewise, operating system, we try and keep the same for quite a while. Mm-hmm. Flight simulation, though, a lot of military customers. So when the government says everybody goes to Windows 10, if this particular real-time extension isn't currently supporting Windows 10, it does, by the way, then that's a problem. So I mean, most of the requirements you can pretty much nail down and say, much like a gaming console, this is it. I don't have to think about other things. But then we get those things like information assurance, cybersecurity that plays a role in determining what needs to be done. Likewise, contracts. People like to come out and say, much like my example, where they don't like Windows, they could come out and say, provide us a solution on Linux. And we can either do a non-compliant bid, we can do no bid, we can say, yes, we want to do this and make everything happen.
Okay. Cool. Thanks.
You're welcome. We're probably about done, 10 minutes. Still time for questions. 9 minutes. Okay. Thank you, everyone.